Okay, hello everyone. I hope you're all healthy. I want to make an announcement before we get started. It concerns the problem sets. So originally we had 5 problem sets for the course. You've already completed 3. We're going to hand out a 4th problem set very soon. It'll be shorter than the others. And then for the 5th problem set, everybody will get full credit for having done a 5th problem set as a bonus for having to put up with such difficult circumstances for the remainder of the semester. Okay, so today we're going to discuss actinide chemistry, and we have an expert, Dr. Dominik Halter, who's been doing research in this area for some time now. And so, Dominik, maybe you go ahead and share your screen and take it away.
All right, thanks and good morning, everyone. It's my pleasure to be here today virtually with you. And in order to not limit my streaming capabilities at home, I will stop my video as we go through the talk. Should you have any questions as we go through the lecture, or should there be any technical problems, please let me know anytime. Just speak up as you have done before. So let me share the screen on the slides with you. And I suppose this should now be on full screen.
Yeah, it looks good.
Thanks for the feedback. So as already introduced, today's lecture will be on the actinide elements, and we will, wherever possible, relate back to last week's lecture on the lanthanides, where we will try to draw conclusions about similarities and differences between the 4F and the 5F elements on the periodic table. Starting off with the natural occurrence of actinide elements, basically only thorium and uranium naturally occur in significant quantities to be mined. And thorium is typically obtained from monazite, a mixed F element phosphate mineral that contains significant quantities of thorium oxide, up to 28% usually, whereas uranium is in most cases or predominantly obtained from pitchblende, also called uraninite. And this mineral mostly contains uranium-4 oxide, but also contains some uranium-5,6 mixed oxides as the uranium-308 shown over here. And due to their natural radioactivity through their decay chains, these elements, uranium and thorium, also give rise to some limited natural abundance of productinium or actinium, as uranium, for example, can undergo the classic alpha emission, thereby lowering the atomic number by 2 for the alpha particle and the mass number by 4, leading us to thorium isotope 234, which then undergoes a beta emission, which converts 1 neutron of the core into 1 proton, so the proton or atomic number goes up by 1, whereas the mass number stays constant, yielding isotope productinium-234. In a similar way, starting from a different isotope, the uranium-235, which is the fissile isotope predominantly used in nuclear reactors, we can get a different isotope of productinium, namely the 231, which can then also decay to yield actinium. And through this way, a variety of daughter nuclei can be generated from radioactive elements. We don't go into all detail of this in today's lecture, but we would rather like to discuss what transuranic elements we also have on the periodic table. The major groups that 5F elements are divided into are the early actinides, the thorium, the productinium, and the uranium, and then the transuranic elements, which are all of them on the right side of the row of the actinides. And the first of which, neptunium, was found in 1940 at the Berkeley Radiation Labs by McMillan and Abelson by using a newly built cyclotron particle accelerator that could be used to bombard a uranium-238 target with a deuteron, so a heavy proton, which can be absorbed. And by simply doing the arithmetics about the atomic numbers and the mass numbers, you can see that by absorbing a proton to uranium-238, we end up with neptunium 238 as this process simultaneously liberates 2 more neutrons. So neptunium was isolated by bombarding uranium with deuterium, with deuterons, but as it only has a half-life time of 2 days, it was very clear that shortly after these scientists had neptunium at hand in Berkeley, they also found plutonium, to which it naturally converted on very short time scale. So this was pretty remarkable times, because due to access to this new piece of equipment, namely the particle accelerator, the radiochemistry possible gave the scientists working with it at the time the chance to find out a whole new series of elements on the periodic table that was not yet known. And today, these elements are typically no longer produced via the particle accelerated synthesis method shown here, but they are more easily and more readily produced by neutron capture in nuclear reactors. A so-called breeding reactor reaction would be to use uranium-238 as a target again, which can then absorb a neutron from the reactor to form uranium-239, which can then undergo beta decay to form neptunium-239, which then gives rise to plutonium-239. And you may realize that both ways to make plutonium, either in the breeder reactor or in the particle accelerator, form different isotopes. And while the different isotopes of plutonium have very similar or identical chemical properties for synthetic chemistry of making plutonium complexes, their radiochemistry is vastly different. So whenever people are interested in synthesizing plutonium complexes, they would rather go to the, first of all, more stable, and secondly, more easy to produce plutonium isotope 239. Whereas when the radioactivity properties are required, the more radioactive plutonium 238 is used. And the radiochemistry properties are summarized in the table below, where you can see that the half-life, so the time after which 50% of a given amount of this radioactivity, of this radioactive material has decayed, is 24,000 years for the isotope 239, whereas it is almost only 90 years for the isotope plutonium 238. And if you have a larger block of this metal, basically the half-life time relates directly to the decay heat that accumulates in that material. So as the nuclear decay liberates heat, the surface to mass ratio of how this radioactive element basically is formed. In this case, for example, as a sphere, or it could be as a block or as a fine powder, will have a huge influence on how hot it heats itself up. So what you can see here in this picture is a self-heated, red-hot glowing plutonium oxide sphere. This is roughly 250 grams of plutonium in a sphere that is a little more than 1 inch in diameter. And because this is the heavily radioactive isotope plutonium 238, the high heat of decay heats it up to be self-heated to red-hot glowing. And this picture was taken by Dr. David Clark, one of the leading scientists we have on the world for transuranics and actinide chemistry. He works at the Los Alamos National Lab in New Mexico. So I will bring his name up several times during the talk, as he is really moving forward our understanding of these remarkable elements. And I thought you should really see his face at least once during the talk. As the slide was pretty busy, I had difficulties on placing him somewhere and felt uncomfortable right next to this red-hot glowing sphere of plutonium. But I think for your education, he is fine with it this time. So once plutonium is generated inside a nuclear reactor through that fission process in a breeding reactor, at some point it needs to be isolated. And the separation of plutonium and uranium from the fission product in spent nuclear fuel is predominantly done by the so-called Purex process, the plutonium and uranium recovery by extraction process. There are several other processes, and this is a big field of research in actinide chemistry, as this is, of course, technically and commercially relevant technology, but this is still the leading process worldwide. So as the name extraction process already indicates, this is a two-phase extraction between an aqueous phase and an organic phase, where the aqueous phase is diluted, or I don't know about the precise concentration in these processes, but I would say moderately concentrated nitric acid, which is used to first dissolve the typically uranium and plutonium oxide pellets that are used in the nuclear reactor as a fuel into uranium oxide nitrates and plutonium oxide nitrates. These are then dissolved in the aqueous phase. By providing this very hydrophobic ligand to these metals, namely the tributyl phosphate, it coordinates to the actinide oxide nitrates in a way that is shown in this molecular complex. By coordinating the phosphate oxide oxygen donor in the equatorial plane, thereby creating some driving force through the long organic linkers or ligand chains for the molecule to go into the organic phase. Whereas the also in the equatorial phase coordinated nitrates have a driving force to keep this molecule in the aqueous phase. So do the oxygen ligands of this metal oxide. And if you count the coordination number, you see we have 6 oxygen donors only in the equatorial sphere, and then 2 more oxygen donors in the axial sphere of this metal ion. So a coordination number of 8 is not unusual for actinide complexes. The world record for actinide metal ligand bonds is a total of 15 in a nitrate hydrated complex. So this is a huge difference to transition metal complexes that can also be exploited in synthetic chemistry. But what is done in this extraction process is then, after both uranium oxide nitrate and thorium oxide nitrate are coordinated by 2 of these linkers, they still stay in the aqueous phase of the nitric acid solution. As the entire mixture is then reduced with iron 2 sulfamate, which is a moderately mild reducing agent, it can only reduce the plutonium, but not the uranium. What that means is one of the nitrate ligands that keeps everything in the aqueous phase is removed only for the plutonium and replaced by a tributyl phosphate ligand that drives the molecule into the organic kerosene phase. So through that selective reduction, uranium and plutonium are separated in the organic and the aqueous layer, and then by a simple separation of these layers, the 2 elements can be separated from each other and the plutonium can be isolated. So once the plutonium is isolated, what is typically done with it? Well, I'm not going into any details of nuclear power production today, nor am I going to talk about nuclear warfare. I want to bring some interesting aerospace application for plutonium to your attention. And what is a very challenging problem is to provide sustainable, long-lasting electricity on space missions, because nobody can simply fly out there and change a battery, let's say, on a satellite. So that's a problem that needs to be treated with care. And NASA has decided to go for so-called radiothermal generators that rely on the so-called Seebeck effect, which is nothing else than a thermocouple in which 2 different metals, for example, iron and copper, or in this case, because it gives a better charge, a better current flow through the cell, is a silicon germanium contact, where the two metals are soldered together to give two junctions. And at each of these junctions, the electrons have a different potential to reside in one metal or the other, as you know it from any other, for example, PN junction semiconductors. And by heating one of the junctions, we provide thermal driving force for electrons to be promoted from one metal into the other. And by cooling the other side, a thermodynamic sink is created for these extra electrons to go to. This creates a current in the material which can be harnessed to for the electricity any device would need. So NASA thought using a heating red hot glowing plutonium rod that would stay hot for hundreds of years would be a pretty good idea to heat up the hot side of such a thermal generator. Whereas everything is in outer space, where the background radiation temperature in outer space is roughly 3 Kelvin. So that low base temperature is ideal to cool the cold side of such a radiothermal generator. And here you can see the construction scheme of such a device, where the inner core is filled with plutonium to heat up one side of the thermocouple. And then on the outside, there is cooling lamella to cool the other side of the thermocouple, thereby generating current. And in this manner, with around 11 kilograms of plutonium, roughly 900 watts of electric energy can be obtained. And this battery, with a half-life of close to 90 years, is only halfway drained in almost a century. So this is a pretty long-lasting battery. And here you can see one of those modules mounted to a satellite to power it up. The other major application for aerospace is to warm up circuit boards. With a very low temperature of around 3 Kelvin in outer space, most electronics stop working. So NASA has addressed this problem by taking only small quantities of plutonium, boxing them up in a radiation shielding little container that is still heat conducting, and then spacing those out equidistantly over a circuit board. In that way, the electronics do not freeze and the satellites still work. After plutonium, the next transuranic element is americium, and most of you probably have seen the most prominent application of americium before. It is ionizing smoke detectors. So these heavily rely on the continuous alpha particle emission of a sealed americium source, which is tied up to an ionization chamber in which a gas separates two electrodes from one another. And once a gas molecule is hit by an alpha particle, the gas molecule ionizes, liberates electrons, and creates ions, and they travel to the respective differently charged electrodes and generate a constant current that is directly related to the particle emission rate, which is pretty constant with a half-life of 430 years. So this working principle is identical to a Geiger counter, which you know can be used to detect radiation by the very same principles. So as soon as dust or smoke particles enter the smoke detector and block the beam of alpha particles, which then no longer ionize the gas separating those electrodes, the observed or the measured constant current between those electrodes drops. The smoke detector can recognize this and set off the alarm. Unfortunately, with a decay heat of around 115 watts per kilogram, americium is not generating enough heat for radiothermal generators, but it is also used as a substitute for plutonium to heat up circuit boards, thereby saving the more powerful plutonium for other applications. since we have now talked about several of these transuranic elements, of course, I want to introduce you to the scientist who rules them all, who basically discovered most of them, Glenn Seaborg, former professor at Berkeley. And he discovered 10 of those transuranic elements during his time in Berkeley, which we are very proud of to have him here, while he was also supervising or leading experiments at Argonne National Lab and over in Chicago during the Manhattan Project. So he was heavily involved in actinide and F-element chemistry back in his time, where we are particularly proud to say that in Gilman Hall 307 back in 1941, plutonium was discovered, which rendered this laboratory a national historic chemical landmark for today. Of course, all his success went not unrecognized, and everybody who has ever used the elevators in Latimer Hall hopefully has seen his plaque for winning the Nobel Prize in 1951 for discovering the transuranic element. But what not all of you may have heard before is that he also has been constant advisor basically, for 10 US presidents from the Manhattan Project throughout until the end of the Cold War, advising on the use of actinides. And basically he has also been the most important advocate to traverse from nuclear warfare applications towards civil applications of nuclear energy production. And all his success manifested in more than 500 journal articles. So I can't emphasize enough how important he is for the field. And I was pretty excited when I learned that I could come to Berkeley as a postdoc now, where as a grad student, I've always admired Glenn Seaborg, and I could now be in the same research facilities as he has been before. That's exciting times for me, and I hope it's also exciting for you. So as he investigated the physical properties and the chemistry of many of the actinide elements, we can have another look at the table showing us their half-lives and their predominant decay modes for the major isotopes. And while we have previously used these measures to determine whether such isotopes can be used, for example, to produce radiothermal generators, from a synthetic chemist perspective, we do not want a short half-life time that gives us a high decay rate. We are more interested in the elements that have a lower half-life, which exposes scientists to lower doses of radiation and simplifies experiments a lot. So a good entry into synthetic actinide chemistry for everyone is typically thorium and uranium chemistry with a half-life of 10 to the power of 10 and 10 to the power of 9 years, with the predominant decay mode being alpha emission, which can be shielded pretty effectively, for example, by working in a glove box. Further physical properties, such as the ionic radii, are very parallel to the lanthanide ions, as you have seen last week, where for the earlier lanthanides, we have pretty high ionic radii in comparison to the transition metals. And similarly, as we proceed through the row, the actinide ions contract, decreasing their ionic radii. And of course, for a higher nuclear charge in the tetravalent ions, the respective ionic radii are further decreased. For the electronic ground state configurations, for actinium, first the 6d1 orbital and the 7s orbitals are occupied with 2 electrons. For thorium, a further electron is placed in a 6d orbital, where for uranium and for protactinium, for the first time, we occupy the 5f orbitals to obtain a ground state electronic configuration. I got chat messages, pardon. Okay, pardon about that, technical problems on my side. So I want to finish this one point quickly. The electron configuration for uranium is 5f3 7s2 6d1, and then as we oxidize it to uranium-3, basically the s and the d orbital electrons are first removed to yield the f3 configuration, and that holds true for the entire series of actinides, where we only have F-only electron configurations. And I think this may be a good point to ask if anybody has any questions. Please speak up. You may, of course, always interrupt me, but maybe if something came up now, you can always.
I have a question about, I guess, so this is like lanthanides, but maybe it applies as well, like the lanthanide contraction. And
Right.
the way that we rationalize that is that there's a low like f orbital like shielding term or repulsion between those two electrons. But at the same time, we say that these ions are pretty, like they behave pretty ionic because the f orbitals are pretty well like recessed into the atom. How do we rationalize those both at the same time? Do you get what I'm saying?
I get what you're saying. So another part of the equation why F element or F orbitals, particularly for the lanthanides, are considered ionic in bonding is because they are also very diffuse. So it is, of course, how far do they extend out, and are they shielded by the core electrons? But it is also how directed are they to give good overlap in organometallic bonding for covalency and bonds. Does that make sense?
Yeah, thanks.
I have another question through the chat box. So it was asked whether if the smoke in the americium using smoke detectors was water steam, whether also a signal would be generated. That is a great technical question, and I think that could be treated by the technical specs of the respective smoke detector. So if it was an open chamber so that the water smoke could enter, of course the water could still be ionized and generate a signal. But if the ionization chamber is sealed, basically the alpha particles should still be blocked from entering the ionization chamber. So I think that could generate a signal, but I'm not 100% sure on this. And probably that also depends on the model and how it's constructed. Since water or steam is a major component of burning something, usually, probably this was taken into account. Okay, another question that I've received through the chat box was, why does the smoke uncharge the particles? So basically, let me see if I understand this correctly. So you're asking how the alpha particles are uncharged. Is that correct? And if so, I would like to respond that the alpha particles are basically kept from entering into the ionization chamber rather than being uncharged or discharged, as you say. So they have a very short free mean path, and that means they are just being blocked from going inside, so they don't ionize anything inside. And if they hit a dust particle or a smoke particle before they can get into the ionization chamber of the smoke detector, they just cannot ionize the gas inside there. Does that answer your question? Okay, wonderful. So if there are no further questions, I guess we can proceed further from here. And from the ground state electron configurations, move over to something that is very dear to my heart, the redox chemistry of actinides, which is represented on this chart by the most stable oxidation states and the accessible oxidation states for the different element. And you may notice this is very different from what we have seen last week for the lanthanide, where it was a safe bet basically to say 3+ is the most stable oxidation state. And if you ever had to guess what complex had, it would usually be a 3+ complex. Here we see this is heavily diverse. Basically, the mid-actinides from uranium through americium show a very rich redox chemistry spanning oxidation states from +2 up to +7, whereas the very late actinides, again, are limited to their +3 and +2 oxidation states. So they start to behave much more like lanthanides again in their redox chemistry, whereas the early and mid lanthanides are very different in that regard. And I would like to take this opportunity to tell you that, of course, textbooks as you get them are not always up to date 100%, so things happen. And one of the additions I want to make to your table as we go through this explicitly during the further lecture will be uranium-2 is by now almost 7 years stabilized oxidation state for uranium. Also, thorium complexes with the oxidation state 3+ are getting more abundant. And I think Frank Leppert also published on a thorium-2 complex. So there is higher redox reactivity on the left side of the actinide. And the second thing I want to mention, last week you have seen a variety of, or basically that the entire series of lanthanide is required to generate a nice rainbow of different colors that can be accessed, where for the actinides, it is efficient enough to just pick the redox active ones, plutonium or uranium, and get a lot of different colors in their different oxidation states. So whenever you look online for actinides, for plutonium, or for uranium specifically, there's no way you will not run across these two pictures we have here on the left side. And as they are usually not referenced to anything, I can tell you I've talked to Dr. Dave Clark from the Los Alamos lab, and he assured me that these pictures were taken at Los Alamos, and he had been involved in having them taken. So you can know that worldwide, these are being referenced as almost the only pictures of actinides you see somewhere. These were taken at Los Alamos. They are driving this research forward for the entire world. So that's great. We have these. Everybody admires this. But what I also want to bring up in that connection is that most of these online references that use these pictures would always tell you the different colors are somewhat characteristic for the oxidation state. And that is absolutely not true. For a quick comparison, I just pulled out some photographs I had left from my PhD times in uranium chemistry. And you can see why, while the uranium-3 over here on the left side is very dark in color, this one is a more purplish color in organic solution. And this uranium-4 complex that I synthesized is a pale yellow. So this is very highly concentrated to make the color more visible. These are often pale yellow, the organometallic uranium-4s. Whereas this one is very dark green. This uranium-5 is entirely colorless, whereas this uranium-5 is red, and this uranium-6 is yellow, whereas this one is a dark brown, almost blackish color. So don't take everything for granted you read online, particularly not with respect to actinide chemistry, where information density is pretty thin already. That's just as a careful note on the side. And with that, I want to refresh your mind on f orbitals. You've seen those last week for the 4 f orbitals. They have additional nodes and more complex shapes than the d orbitals that you are typically used to work with. But what I want to bring to your attention that whenever any actinide or F element chemistry is discussed, typically you see a picture like that also for the actinide. Of course, you all know that as we increase the quantum number and go from the 4f to the 5f orbitals, we also need to add another node to these. So the 5f orbitals are not only larger, they also have an additional radial node, and some minor probability for the electrons to reside closer to the core on the inside. It is, on the other hand, already very complex to look at these orbital diagrams or at these graphical representations of the f orbitals. And it is commonly agreed that the outside electron, or the electron density that propagates outside of the core electrons is identical to what it looks like for the 4f electrons. So when discussing orbital overlap or symmetry, typically people refer to the 4f orbitals and neglect the higher complexity of the 5f orbitals for simplicity of discussion. But you, of course, know that that life is not always that simple. We just make those simplified models to be able to talk more easily about even more complicated things that rely on that. And bringing back the radial distribution plot that you've seen on the f orbitals last week, we can actually see that extra radial node that we've just seen in the picture on the last slide inside the radial distribution plot too. And you can also see that due to their larger radial extent, they extend the f orbitals in 5f shells, extend further beyond the core electrons, and can therefore be involved in organometallic bonding and have actual overlap with ligand orbitals. Whereas we had this in the question that was asked before, for the 4f elements, they are pretty much shielded and hidden inside the core electrons, which render the bonds more ionic. And this could be a good place to stop and ask if there are any further questions by anyone in the audience this far. So please speak up. All right, if that's not the case, then we will just go ahead and see how the differences in the radial extent and in the metal ligand bond covalency manifest in orbital splitting diagrams. And this was done recently by Wayne Lukens working at the Lawrence Berkeley National Lab by experimental and quantum chemical methods for this uranium tris-CP complex, where these cyclopentadienyl ligands are really the workhorse for molecular uranium and actinide chemistry. So in this case, all of the 3 CP ligands are in the same plane, basically, with the centroid of those being on one circle around the metal ion. And this kind of ligand environment creates an orbital splitting that has roughly 6,000 wave numbers from the lowest lying f orbital to the highest lying f orbital because of the increased extent of the f orbitals and the better covalent overlap with the ligands. If the same complex is synthesized with a neodymium 3+ ion instead of a uranium 3+ ion, the orbital splitting only spans roughly, or the energy splitting roughly spans 3,000 wave numbers due to the less covalent and smaller f orbitals of the 4f shell. So if we plug that information back into the master plot you started generating last week in the lanthanide lecture, we can remind ourselves that for transition metals, the crystal field splitting is the predominant factor to separate energetic states, and that spin orbit coupling only plays a very minor role. For the F elements, for the 4F in specific, this trend is reversed, where due to the larger nuclei, electrons orbiting the core approach relativistic speeds, and spin orbit coupling plays a major role. And actually, due to the low covalency in metal ligand bonding, plays a larger role in crystal field splitting. As we move from 4F lanthanides to 5F actinides, the nuclei are even larger, which means that the spin orbit coupling is also more pronounced than for the 4F lanthanide. And as we learned and have recently seen, due to the increased metal ligand bond covalency, also the crystal field splitting is a lot more pronounced than for the 4f orbitals. And in this manner, shown on this plot, you can easily see that due to larger crystal field splitting, different spin orbit coupling separated states also start to overlap in their energy states, creating a very rich electronic structure that can get very complicated very quickly for the different actinide ions. So if you imagine one electron in the ground state of this complex, for example, you can excite into a whole variety of different accessible electronic f orbital states in so-called FF transitions. And we want to look at those in electronic absorption spectra for the different actinides. So each of these spectra consists of two sections which have two individual molar absorptivity axes or molar extinction coefficient axes. So for the FF transitions on the right, we have our axis right here, and it ranges up to 120 liters per mole centimeter. And as you look at these FF transitions plotted for the different actinide ions, you can recognize that similar to the lanthanides, which you have seen last week, these are pretty sharp transitions of low intensity. And the rationale is still the same. Transitioning from an f orbital into another f orbital does not change the symmetry and therefore does not comply with the Laporte selection rule for the process. So these are Laporte forbidden processes, rendering them low probability and therefore low intensity in the electronic absorption spectrum. So these are pretty weak, which you can particularly see here for the later actinides. And in addition, the energy range for those transitions is not suitable to couple to vibronic states, which renders these transitions really sharp. As you have seen in the orbital splitting diagram on the last slide, even though the crystal field splitting is more pronounced than for the lanthanides, the overlap between all the states from also higher lying spin orbit coupling states generate a variety of transitions which overall end in low energy separations between all the different accessible states, which moves the FF transitions into the near IR or lower energy range of the electronic absorption spectrum. I think there was quite a lot of information so far. Are there any questions on this? All right, there's something coming up.
Sorry, I had a question. So spin orbit coupling is like would result in broader peaks. So we know there's not a lot of that because, or I'm sorry.
That's an excellent point that you bring out there. So with the increasing spin orbit coupling, the 5FF transitions are indeed more broad than for the 4FF transitions. So we do see influences of that. Does that answer your question?
Yes, it does. Thank you.
Okay. Could you explain one more time why actinates can make better covalent bonds? Oh yeah, of course. So it's a shame that I don't have a board to draw on. That would be perfect now. So if you imagine what a covalent bond is, basically it is the overlap between two lobes of different atomic orbitals that then generate a molecular orbital, or basically two molecular orbitals for each bond, one bonding and one anti-bonding. And the quality or the strength of that interaction, so the covalency, is directly related to the different energy levels of the two orbitals that you mix. So if they're very, very different in energy, they have a hard time overlapping on the energy level scale, which creates a very weak bond. And the second parameter to judge is the physical overlap. So in space, the orbital lobes actually need to overlap to create a bond. And you can easily imagine if the orbital lobe does not come out of the shell of the core electrons of an atom, it is really hard for these orbital lobes to make good overlap with ligand orbitals to make a bond. Whereas for the actinides, where these orbital lobes extend further out and can actually reach the ligand orbitals, they can make better bonds because they actually physically overlap much better. Does that answer your question? Okay, great. There are no further questions on this for now. We can proceed. Okay, there we go. So after we've talked a little bit about the FF transitions that arise from the crystal field splitting, we can make things even more complicated by also taking into account that 6d orbitals are close in energetic proximity. And as you remember from the electronic ground states of the elements, actually those 6d orbitals are even filled. So they are definitely not far enough away to not interact with the electronic states. So you can imagine to also do some spin orbit coupling on those 6ds and then do some crystal field splitting on those 6ds, and you will easily realize that in between of all these 4 F states that we already have, we generate additional 6d states. And that gets really complicated really quickly, so we're not overcrowding this graph by doing that, but I just want you to bear that in mind. When we go back to the electronic absorption spectra, where we now exemplarily look at the plot for the uranium spectrum again, where on the left side, with the axis showing the higher extinction coefficient range, we see the FD transitions plotted, where ground state electrons residing in an F orbital state can be excited into D acceptor orbitals of the right energetic range. And as we change the symmetry, going from an ungerade F orbital into a gerade D orbital, these transitions are now Laporte allowed and therefore have a much higher intensity than the FF transitions. For these plots, obviously the FF transitions are amplified, so they look even larger, but you can see they are in the range of like 60 to 120 liters per mole centimeter, whereas these FD transitions are in the range of 1800 for the highest of these. And you can also see that while we have a very sharp pattern signature for the FF transitions that are not vibronically coupled, the FD transitions are in the right energy range to heavily vibronically couple with vibrations of the lattice of either a crystal or a solid state material that contains actinides or the ligand environment of a complex. And in order to derive crystal field splitting and the electronic structure of such compounds or materials, or basically the actinide ions contained in these elements, in these materials or compounds, the UV-Vis spectrum or the electronic absorption spectrum can be recorded at low temperatures as low as 7 Kelvin or 5 Kelvin using a liquid helium cryostat to freeze out vibrations entirely. So even though energetically it would be possible for those transitions to couple to vibrations and broaden them, there no longer are vibrations because of the low temperatures. And that sharply resolves all these FD transitions, allowing to model them and to understand the electronic structure. So I think this is a bit beyond the scope of this lecture, so we'll leave it at there, but you know that this can be done. To summarize what we've talked about now, the valence 5f orbitals of lanthanides of actinides extend further than for the lanthanides, so we can have more covalent bonding. We just discussed this during the question. As a result, the orbital splitting due to crystal field is much larger than for the lanthanides. And as we also discussed, as a further consequence for the larger nuclei, the 5F transitions are broader than the 4F transitions. And as we've just looked at them, the 5F6D transitions, as they are Laporte allowed, have much higher extinction coefficients and typically range in the visible to UV spectrum, whereas the FF transitions are in the near IR spectrum typically. Finally, I want to go back one more time and discuss one more trend on these electronic absorption spectra, namely that in the FD spectral range, you see an obvious trend when going from uranium to neptunium to plutonium to americium. Basically, what we see is that the average maximum where these absorptions are observed shifts to higher energies, or in this case to lower wavelengths, and that the overall intensity is decreased for the later actinides. And we want to use a very oversimplified molecular orbitals scheme that was previously produced and published to understand these trends. So what happens for, again, cyclopentadienyl complexes for which these orbital splitting diagrams were calculated, the f orbitals are stabilized when going from thorium to protactinium all the way over to plutonium. So across the series, the f orbitals are more and more stable and therefore lower in energy. The crystal field splitting of this particular ligand environment renders the DC square orbital that is closed to be the lowest accessible d orbital that the f orbitals, or basically the electrons, could interact with. This leads to a calculated, I must say, ground state configuration for the thorium complex of 6d1, where the valence electron is actually placed in the d shell rather than the f shell. However, as we traverse through the series, these d orbitals are less and less stabilized, and therefore get higher and higher in energy. Where at uranium, we have the very special case that the f orbitals and the d orbitals are almost identical in energy, which creates an exciting opportunity, or raises the question, where do electrons actually go? And in this particularly challenging and flexible, ground state flexible case, what happens to molecules in respect to different ligand fields? Where for the late actinides, then, there's no longer a question that the d orbitals will be occupied. This will all be pure f ground state. Is there any questions on this orbital diagram so far? Otherwise, I will just proceed. So as I already raised, one of the major questions that was there was, first of all, can uranium-3 be reduced to uranium-2? You have seen in the chart early in the lecture that this was for a very long time not the case, and uranium-2 could not be stabilized. But the theoretical question was also, if we add another electron, so a fourth electron into that system, will it go into the f orbital or will it go into the d orbital? And what can we maybe do with the ligand field to tune this and better understand how f and d orbitals in actinides react to changed orbital environments of different ligand fields? So the first uranium-2 complex was synthesized in 2013 by Professor Bill Evans at UC Irvine, one of the major drivers for molecular actinide and lanthanide chemistry for many decades now. And so what he did, he synthesized a very prototypical uranium-3 cyclopentadienyl complex, where he added one trimethylsilyl group per CP ring to add some additional steric bulk to the ligand to protect the center uranium ion from decomposition, for example, by interaction with solvents after a very highly reactive uranium-2 species is synthesized. And he, or better, his group, successfully reduced this molecule with potassium graphite in the presence of 2,2,2 cryptant, where you can see the complex cation potassium in 2,2,2 cryptant depicted here. So the purpose of this is to prevent any contact interaction between the potassium and the uranium to perturb the electronic structure. and they could crystallize their new uranium-2 complex, where I would like to bring to your attention that it is very remarkable that when changing the oxidation state from 3 to 2 and changing the electron density and the Coulomb interaction between negatively charged ligands and positively charged metal ions severely, the overall molecular structure or the geometry of the complex barely changes at all. It's almost invariant. So we will come back to that later. Please bear that in mind. Since we talked about electronic absorption spectra a lot before, this is also how the Evans group identified the electronic ground state of this molecule. They recorded an electronic absorption spectrum, looked at the range where FD transitions are expected, and then used quantum chemical calculations to model this electronic absorption spectrum. So now for probably transition metal chemists, you might think this is not a really great agreement between the calculated spectrum and the experimental spectrum. But for actinides, things are pretty complicated. And what they have basically done to identify the ground state is they have calculated a UV-Vis spectrum for the 5F3-6D1 configuration, which they expected for the SEP ligand environment, overlaid it with the experimental spectrum, and then did the exact same thing, calculating an electronic absorption spectrum for a 5F4-6D0 ground state. And there was no agreement, it was a very different spectrum. And based on that rationale, they identified their ground state to be 5F3-6D1. And what the quantum chemical calculations also did was they allowed to show the electron density cloud of that additional electron they added onto the metal center. And you can easily see from the shape that this really looks like a d orbital as their highest occupied molecular orbital. And at the center of this slide, I have drawn a little cartoon or ChemDraw figure to illustrate the orientation of the entire molecule and this additional electron in a different angle. So basically, we still have all the 3 CP ligands in one plane, and the DC square orbital is basically threaded between these, perfectly shielded from all directions, and not interacting with the ligand sphere at all, which basically isolates this electron. And to the surprise of the Evans group and basically everyone in the actinide community, this stabilizes this additional electron so much that the uranium-2 complex is actually pretty stable. And even when they wanted to react it with multiple substrates, it really didn't want to react. So this is a really stable complex. And what the DFT model also revealed is, of course, a qualitative orbital splitting diagram, where you can see that the 6 DC square is right in between all the other F states and the lowest lying that can be populated with an additional electron. Does anybody have any questions to this example on the uranium-2 complex? Okay, great. If that's not the case, then we can proceed. So one of the first projects that I worked on as a grad student was, can a uranium-2 complex actually be synthesized with a 5F4-6D0 ground state by tuning the stabilization of these basically core orbitals, or the valence orbitals that are that are involved in the reaction, basically. And what we tried was to have a look again at the orbitals that are involved in the reaction and move away from classic CP ligands to change or influence the electron configuration by orbital interactions. And you can easily see that with the different f orbital geometries we have available, we can make sigma bonds, we can make pi bonds, we can make delta bonds, and we can even make very exotic phi bonds. So in order to harness these, we decided to use benzene rings or aromatic systems, simply because their pi star orbitals have the perfect symmetry to engage both in delta bonding and phi bonding interactions with the respective f orbitals of uranium ions. Having the idea of attaching a uranium ion to a pi system is not as easy, so we decided to do this by adding phenolate linker arms onto an arene ring that would then help to lock a uranium ion right here into place and basically force an electronic interaction between f orbitals and the pi star orbitals of this ligand backbone. And last but not least, it was definitely crucial to the stabilization of the previously shown uranium-2 complex to have steric protection for this molecule to prevent the potentially highly reactive uranium-2 ion from decomposition. So for this purpose, we decorated adamantyl groups onto the phenolate ligands, which created sufficient steric protection. And what is introduced to you in less than 2 minutes on 2 quick slides actually took the postdoc life of 2 postdocs and some of my work time as a grad student to finally synthesize this ligand by itself and then successfully synthesize the uranium complex. So we were very relieved when after severe effort, we finally had this molecule in hand, we could crystallize it, see everything worked as planned. And when quantum chemical calculations indeed confirmed to us that we have a very covalent overlap between the f orbitals and the pi system of the arene backbone as the start to basically do what we wanted to do from the first place and stabilize these f orbitals. With the uranium-3 complex in hand, we finally successfully achieved the chemical reduction under identical conditions to what the Evans group had done with potassium and 222 cryptand, and we could isolate our uranium-2 complex also with a non-coordinating potassium ion encrypted. And we quickly realized that the uranium oxygen bonds severely change from 2.18 to almost 2.24 angstroms. So that is expected as we increase the electron density around the metal center. It no longer wants to interact as strongly with the negatively charged oxygen donors. So these move away. And the second trend that made us very happy was that upon increasing the electron density, the distance between the uranium ion and the centroid of the arene backbone decreased. So the additional electron density we provided was redistributed over the pi system and strengthened the uranium arene interaction, moving this uranium ion closer towards the pi system, away from the usually preferred strong oxygen donors. And quantum chemical calculations on the exact model system indeed confirmed to us that the additional electron that we added is sitting on the uranium ion, and it does have the symmetry of an f orbital. Whereas the lower lying electrons were heavily stabilized by very, very covalent interaction with the ligand. And what this meant is basically coming from the initial uranium-2 system, where the additional electron was fully isolated from everything, and the d orbital was stabilized by the ligand sphere. In our newly created ligand environment, the d orbital is no longer stabilized, therefore higher in energy, whereas the lower lying, whereas the f orbitals are now heavily stabilized by covalent interactions, moving them down in energy to create a qualitative orbital diagram in which no longer d orbitals are occupied by this extra electron, but an f orbital. And in addition to delta bonds, which I personally consider really cool, we successfully also achieved a phi bond in this molecule, and organometallic phi bonds are extremely rare and even more cool if you ask me. So we were quite happy after many years of trying to finally have succeeded with that. Are there any questions on the second uranium-2 complex?
How common are phi bonds just in general?
They're not common at all. That's the entire point. I mean, there's not much known about it. There's we'll see another example of phi bonds with actinide towards the end of this slide deck, but I'm not aware that there's like more than a handful published so far. So these are very rare. So every example that we get helps us to better understand how we can make these and what these introduce in electronic structure and reactivity to a molecule. That's why we were so excited, because they are so rare. So as said, back in Erlangen, we were super happy to have made our phi bond, to only realize that, of course, at Cal, almost 50 years earlier, Andrew Streitwieser has already synthesized and proposed a uranium phi bond with a pi system. Andrew joined faculty, I don't know the exact date, but with the intention to study molecular orbital interactions and MO diagrams. He's been a major driver to develop the concept. And of course, with that mindset, he was very curious what would happen if one were to team up a large pi system with many accessible electrons with the incredibly weird orbital geometry and all the possibilities arising from uranium f orbitals. So he strived to synthesize uranocene as an analog to ferrocene, one of the most famous organometallic transition metal complexes. And as he succeeded in synthesizing uranocene, he was definitely celebrated as one of the rock stars in actinide chemistry. At least back in my grad school times, everybody was talking about him and uranocene, one of the most important and one of the first organometallic actinide molecules that were ever made. And he published that in 1968, already proposing all kinds of orbital interactions that I described to you earlier in this talk, even though he didn't even have a single crystal structure of that molecule. Please bear in mind that was 1968 that he published this. And so what he had was basically magnetic structures and I think some mass spectrometry. And he just concluded that he probably had that molecule and expected what would happen there. He synthesized reduced cyclooctatetraene ligand by reacting with potassium to obtain the, by now famous, I would say, COT ligand dianionic, which is flat due to its aromaticity of 10 pi electrons following the Huckel rule. That was straightforward. And of course, uranium, as it is very large, could not form uranocene with a regular CP ligand, or rather two regular CP ligands, because it is simply too small to fill up the entire coordination sphere. And uranium too, back in the day, also was a very long shot. So by using this dianionic ligand, reacting it with uranium tetrachloride, he could synthesize a happy and stable uranium-4 complex that would also have the planarity and the aromaticity of ferrocene, therefore calling it uranocene. And it was not until Ken Raymond joined the faculty in 1968 where Andrew thought of the idea that is the perfect opportunity to get a single crystal structure on that molecule, given that getting a structure was not as simple as today. It could easily take 2 weeks for one molecule to solve the structure by hand. And as Ken was known as one of the most talented single crystallographers back in the day, Andrew decided to approach him in the faculty club and just propose to him, I have made this new molecule and I think the structure is really interesting. We want to find out what it does to molecular orbital splitting, and we really need confirmation what it is. Do you think we could get a single crystal structure? And as they were discussing, and of course, things are not always that straightforward and easy, Andrew took out a vial of obviously radioactive and obviously pyrophoric uranocene out of his pocket at the faculty club, containing the most beautiful single crystals that you can imagine, showing them to Ken. And of course, he could not resist, and the crystal structure was immediately obtained and published shortly after, where basically all the initial claims and intentions that Andrew Streitwieser had were confirmed. The molecule was planar as expected. And after that, not much happened on the Uranocene scene until 10 years later, they teamed up making themed t-shirts for the occasion and celebrated the 10 years anniversary of Uranocene. But on the science side of things, the next thing that would happen was probably one of our grad students, Alex, producing a nice video for you that would show you the beautiful structure of Uranocene, the perfectly planar and parallel CP ligands with a linear geometry in a fully eclipsed conformation, generating a DH8 point group symmetry. I think this molecule is incredibly beautiful, and I admire Alex's skills to make this beautiful video. So I hope you enjoy this as much as I do. But of course, there's more science to come on this side. And it was not until 2014 that the usual suspects at the Lawrence Berkeley National Laboratory, in this case, including Stefan Minassian, who I guess did the work, together with people from Los Alamos, and again, here we see Dave Clark and Stosh Cosimore, have worked on elucidating how the electronic structures of Uranocene and also Thorocene, where the uranium ion is changed for thorium, would behave. And very surprisingly, there is some phi bonding interaction for the uranium, but it is almost negligible. You can see there is some orbital, like there's electron density where it's supposed to be for phi symmetry, but it's not really spanning across the entire molecule. Whereas for thorium, there is full covalent, very strong phi bonding interaction across the entire molecule. And that was not only confirmed by quantum chemical calculations, but also by electronic absorption spectroscopy. So the most important takeaway from that slide, of course, is that Cal has done it early and Cal rules, but it is also that 5s elements are very unpredictable. And if you have some almost identical actinide complexes of neighboring atoms, they can be very different in their electronic structure, and actinides will always surprise you. Are there any questions on the Uranocene and Thorocene for now? All right, then I will approach the end of this lecture with just briefly introducing you the synthetic chemistry potential without diving too deep into any details. I just want to get you excited what the physical and electronic properties that we have looked at during this lecture are now used to in designing reactivity. So one of the more recent and most exciting examples from my perspective is the room temperature synthesis of ammonia from nitrogen and protons. I got a message, but my computer won't let me access it. Go Bears. Oh yeah, I should have said that and brought it up. That's right. Alrighty. So we stick to the first example first. So while this structure of this molecular uranium complex is very difficult and intricate, we want to focus at the main feature, which is it has two uranium ions, one here in green on the left side and one here on the right side. And they are both uranium 3+, which means both of them still have 3 valence electrons to spare. And in one chemical reaction, they team up and deliver those 6 electrons to dinitrogen to reduce it to N3-, formally, of course, in multiple electron or proton coupled electron transfer steps, to react with protons to form ammonia. Unfortunately, that reactivity is not yet catalytic, But of course, the actinide community is working on that. That's one of the major roadblocks, that most of the interesting reactivity is unfortunately not catalytic yet. So we need to understand more of the electronic structures and influences of ligand spheres to convert it towards catalytic applications. A second example that is quite remarkable is the carbon-carbon bond formation using one of the most stable molecules we have with a carbon-oxygen triple bond. So carbon monoxide activation is extremely challenging, and at temperatures as low as -70–80 degrees, so without any thermal activation, basically, two of these uranium ions come together and deliver 1 electron each to go from uranium-3 in complex 1 to 2 uranium-4 ions in complex 2, bridged by this deltate 2- ion, forming carbon-carbon bonds and carbon monoxide. This reactivity was driven further to make even larger and larger rings out of carbon monoxide using uranium, but also that is unfortunately not yet catalytic. Another example is from the Meyer group involving the ligand environment that you have already seen for the design of the uranium-2 complex. And this is the first example where uranium complexes were used for electrocatalysis, namely to make hydrogen from water. And while these previous examples have used 2 uranium ions per complex to team up in redox reactions, in this complex, it is actually the case that the uranium ion teams up in redox reactivity with the redox active ligand backbone. So it seems to be good to get cool, fancy reactivity out of uranium to team them up with multiple redox active centers. And the last reactivity that I want to highlight on this brief slide is the borylation of arene CH bonds, where you have seen the kinds of covalent interactions that can occur between uranium ions and the pi system of arenes. And in this particular case, the uranium ions activate the CH bond of an arene that is activated in this inverse sandwich complex geometry, as this is called. So a regular sandwich complex, as ferrocene, for example, has two aromatic systems on the outside and 1 metal in the inside. But what uranium really prefers to do is this inverse sandwich type geometry, in which 1 arene is bridged by 2 actinides. And then it can readily be borylated. It can also be silylated, and some other sort of reactivity has been harnessed. If you're interested in that chemistry, we are very proud that we could recruit Polly Arnold to come over to Berkeley Lab and be now the head of the chemistry facilities there. So she brought her group over from the United Kingdom, and we now have her available. If you're excited in uranium chemistry, you should totally take advantage of all the opportunities we have at Berkeley. It is a very rare occasion that a university provides these opportunities to get involved in actinide chemistry. And if some of you are actually interested to get your feet wet in actinide chemistry, well, more figuratively, of course, you don't want to do that in real life. You want to learn how to start actinide chemistry, and the basic precursors used for all actinide chemistry that was shown in this talk, or the uranium chemistry, basically follows this general protocol. So starting from there, you're basically good to go to run your own experiments if you join a lab that does it. So as uranium is no longer sold for most chemical vendors, you typically need to prepare everything from scratch, starting with buying very hard drill bits using a power drill and a solid block of uranium that sometimes, if you ask around, you can get it from suppliers for nuclear power plants, or you can get it from national labs potentially. You drill uranium turnings that you can further activate by briefly washing them with nitric acid, getting them into a glove box, where these are then reacted with elemental iodine, either 1.5 equivalents for uranium tris iodide or 2 equivalents for uranium 4 iodide. That is one of the major precursors for organometallic uranium chemistry. And if you want to do other reactions that require internal bases, the other major workhorse of uranium chemistry is uranium HMDS that can easily be obtained by reacting sodium hexamethyl disilicide with uranium triiodide. So with these at hand, the future of uranium chemistry is now definitely in your hands, and I hope that some of you choose that exciting path for your future careers. And I think we just landed on time. If you have any questions, let me know now. If you have to leave for other lectures, of course, you're free to go. And then everything else can be discussed in the upcoming office hours. Thanks for joining today.
Okay, thanks very much, Dominic. Any last questions before we adjourn? All right. Well, everybody have a great rest of the day, and we'll on Thursday we'll pick up with starting to learn about porous materials and metal organic frameworks. Bye, everyone.
All right, bye.